So whenever we have a number of resistors in series, it is typically very simple to solve the voltage across each of those resistors by using what is called voltage division. So let's take a look at how this rule works essentially. Let's go ahead and consider a general case where we have, let's say, n number of resistors in series, and I will call this voltage here V. I will call this resistor R1, I will call this resistor R2, I will call this resistor Rn. And now we will call this voltage here V1. We will call this voltage here V2. And I will call this voltage here Vn. Voltage division essentially tells me that the voltage V1 will equal the source voltage, or the voltage across the terminals of the entire series branch, times the resistor of interest. So V1 is resistor of interest will be R1, divided by the total resistance. So in this case, that'll be R1 plus R2 plus all the resistances up to my nth resistor. At the same time, if I want to look at V2, I can say this will be V times R2, because now R2 is the resistor of interest, divided by the total resistance in the entire series branch. Therefore, in general, if I want the nth voltage, I will multiply it by the voltage across the entire terminals. And I will take the resistor of interest as Rn, which is the resistor, again, like in the nth case, I want it across this resistor here. Therefore, Vn will depend entirely upon Rn in the numerator, and then the total resistance in the denominator. Now, it's worth noting that essentially what this is solving the total current through the branch and multiplying it by the resistor all in one step. So really this is a combination of Ohm's law use it in two different steps, really putting it together. So if you look at this highlighted term now, this highlighted term is essentially the current, because it is my total voltage V divided by my total resistance R1 plus R2 plus all the way up to Rn. And so we can generalize the voltage division as the multiplication of the terminals. So my terminal voltage here, or my voltage across the entire branch, I should say, is V. Now notice this is not a source, so this applies for any branch. This can be any branch that is a sub-circuit or a subsection of a larger circuit, and I can still divide the voltage so long as I know what this voltage is between one point and the next. So now let's take a look at a very simple numerical example. And so in this case we have 3 resistors in series, and we have ground. Here we have plus 5 volts, so this will act as my sort of terminal voltage, or my voltage across the all 3 of the resistors. Here I have 1 kilo ohm resistor, here I have a 2 kilo ohm resistor, and here I have a 3 kilo ohm resistor. Now the voltages that I'm interested in are the voltage here, I will call V1, as well as the voltage here, and I'll call this V2. Now, one thing we should note is whenever a voltage appears like so, we are assuming this is the voltage between this point and ground. So the assumption is that I will always have, if we can rewrite this then, a sort of ground point here, and that I will call the voltage between this point and this one V1. Now the thing is, we won't want to draw this every time because it will become very messy very quickly, so I assume whenever I have a sort of branch off like this at any node, and I write a voltage here, that this is the voltage between this point and ground. So now using voltage division, we can say that V1 will equal the voltage across, well, the voltage between this point and ground. Now the voltage between this point and ground will depend on all the resistances between this point and ground. Therefore, the resistances between this node here and ground are 2 and 3. So I will have 2 and 3 in my numerator, and I will have the total resistance in the denominator. So I must have, first of all, my source voltage is 5. Now the resistances between this node here, let's give it a name. This node A and this node B, right now we're only concerned with A. So the resistance between A and ground is 2 plus 3, And this will be divided by 1 plus 2 plus 3, because now this is the total voltage. If you go back to our generic case, it was the voltage, or it was the resistance, R1 plus R2 all the way to Rn. So it's the total resistance here. Now the total resistance here is simply 1 plus 2 plus 3. Now multiplication of this and actually dividing this out, you will find that V1 is 4.17 volts. And so this is my value for V1. Now, for V2, I will do the exact same thing. I will consider this node, let's call it B, and I will consider all the resistance between B and ground. The resistance between B and ground is simply 3 kiloohms, so I will write that V2 is going to equal 5, which is my total voltage between the top and, or the entire branch voltage, I should say, with respect to ground. And this will be multiplied by 3 divided by 1 plus 2 plus 3. When you multiply this out and divide it, you will find that this voltage here is 2.5 volts. And so there we have it. We have our voltages V1 and our voltages V2. And so you can see that voltage division is essentially Ohm's law. You use Ohm's law twice, once for the current and then you find it again for the voltage of interest. So we're pretty much doing an Ohm's law of the total branch, and then we're doing Ohm's law for each particular resistor, or you know, in the case of A, it's the sort of sum of the two resistances. So that's it for voltage division. In terms of any more complicated concepts, we will use complicated questions, we will use the exact same procedure every time. We will see in the superposition video that voltage division can be done using both positive and negative sources, and sometimes we have to consider voltage division happening across, well, you'll have the superposition, or the overall voltage, let's say at V1, will be the result of two different voltage divisions. But more on that in the sort of next videos. I hope you found this one useful. If you haven't already, hit the subscribe button so that we can get notifications to you as soon as videos are uploaded, and we'll see you in the next one.